Today, we're going to pull back the curtain on the internet itself. We're talking about the invisible set of rules that honestly runs our entire digital world. It's called the TCP IP model, and it's fascinating. I mean, really think about it for a second. You hit send on an email, and boom, it shows up in an inbox halfway across the planet. How does it know where to go? How in the world does it not just get completely lost out there in the digital void?
Well, it's not magic, that's for sure. It's all thanks to this incredibly smart system. You can almost think of it like a digital postal service. It has really specific rules for how to address, pack, and ship every single piece of information we send online.
So, let's start with the first huge problem the internet had to solve. How do you get totally different computers, made by different companies, running completely different software? How do you get them to understand each other? The answer is something called a protocol. And a protocol is just a fancy word for a shared language. It's a set of ground rules that every single device agrees to follow just to make sure that when one computer sends a message, the other one can actually, understand it. And you can see why this is so important, right? Without these common rules, it would just be total chaos. It'd be like one computer trying to speak in an old code like ASCII and another using something modern like Unicode. They'd just be shouting digital gibberish at each other. The signals would be there, but no real communication would be happening at all. Okay, so how do these rules actually work? Well, the best way to get it is to follow a single message on its journey. Imagine you're carefully packing something valuable for a long trip, and every step of the way you're adding another layer of packaging and another set of instructions. So our message is going to travel down this stack of 5 different layers. It starts right at the top, gets passed down, and each layer adds its own special wrapper. And here's why that's so brilliant. By separating all these jobs, you can change one layer without completely breaking all the others. It's a truly revolutionary design. It all starts with you, right here at the application layer. When you're writing an email, your app is using a protocol called SMTP. Or when you're browsing a website, your browser's using HTTP. This is the layer that all the apps we use every day talk to, and it's where the message gets created. Next up, your message gets handed off to the transport layer. Think of this layer as the quality control manager. It takes your big email, chops it up into these smaller, much more manageable pieces called segments, and then it slaps a number on each one so they can be put back together in the right order when they arrive. Now we're at the addressing department. The network layer grabs every single one of those segments and adds the most important piece of information, the IP address of the final destination. This is like writing the full street address on the envelope. And once that address is on there, it's officially called a packet. And this next part is really clever. We add a second address. See, the data link layer doesn't really care about the final destination. It only cares about the very next stop on the journey, like the next router down the line. So it adds this local hardware address, it's called a MAC address, and some error checking data. Now our packet is wrapped up in what we call a frame. Finally, we hit the bottom. The physical layer takes that fully packaged digital frame and does something amazing. It turns all those ones and zeros into a real-world signal, an electrical pulse in a cable, a flash of light in a fiber optic line, or a radio wave flying through the air. And just like that, the message is on its way. Okay. Our package has been sent. So how does this cleverly wrapped and addressed frame actually navigate the huge, complicated web of the internet to find its way home? So to really get this, you have to understand the difference between these two addresses. The IP address is the big picture. It's the final home address on the main package, and it never, ever changes. The MAC address, though, that's just for the very next step. Think of it like the address of the next specific post office branch it has to go to. That local MAC address gets ripped off and updated at every single stop or hop along the route. And the devices doing all this work are routers. They're basically the postal workers of the internet. A router gets the frame, it looks at that unchanging IP address to figure out the best way forward, and then it just slaps a new MAC address on it to send it to the very next router in the chain. So after hopping across who knows how many networks, our message finally arrives at the destination computer. The trip is over. But now the real magic happens. It's time to unpack the message. And yeah, you probably guessed it, this is the exact reverse of the packing process. The physical layer turns the signal back into a frame. The data link layer rips off its wrapper, checks for errors, passes it up. The network layer confirms the IP address is correct, removes its header, and on it goes, all the way back up the stack until your original email is perfectly put back together. Okay, let's jump back for a second to that quality control manager we talked about. the transport layer. Turns out, it actually has two totally different ways of doing its job. Two shipping options, you could say. They're called TCP and UDP. This table really breaks it down. So on one hand, you've got TCP. Think of this like sending a certified package with tracking. It sets up a formal connection, it numbers every single piece, and it guarantees they all get there in the right order. It's perfect for things like email or file downloads, where every single bit has to be perfect. But then you've UDP. This is more like throwing a postcard in the mail. It's way faster. It just sends the data without any guarantees. You just fire and forget. And this is great for stuff like video streaming or online gaming, where a little bit of data loss is no big deal, but speed is everything. And this quote just sums it up perfectly. It's a trade-off. TCP gives you reliability, but it's a bit slower. UDP gives you incredible speed, but it's less reliable. The application you're using just gets to choose which one it needs more. So, after hearing about all these layers and rules, you might be thinking, why is it so complicated? Well, it turns out it's precisely this layered design that makes the whole system so unbelievably elegant and powerful. The true genius of the model is right here. First, it's modular. Each layer has one job and it does it well, which makes everything easier to manage. This creates interoperability, which is why a brand new phone can talk to a 20-year-old server, no problem. It's also incredibly resilient. If one path on the internet goes down, routers just find a new one. And finally, it's just massively scalable. The same exact model runs your little home network and the entire global internet. So the next time you stream a movie or you're on a video call with someone across the world, just take a second to remember this invisible dance that's happening behind the scenes. This whole layered, rule-based process is the fundamental architecture that makes our modern, connected world even possible. And that leaves us with one last pretty fascinating question. This brilliant system has served us incredibly well for decades, but technology never, ever stands still. So as we head into an age of AI and quantum computing and the metaverse, what will the rules of the road need to look like for the next generation of the internet?